So my name is Simona Capponi, and I'm a PhD student at the University of Liverpool. And today I'm going to describe the work that I did with my group about batch Bayesian optimization for the optimization of molecular properties applied to small organic molecules. So I think that by now it's quite clear that Bayesian optimization is a very good tool for this kind of problem, but I just summarize shortly here. So why Bayesian optimization for these optimization problems? Because actually Bayesian optimization is good in addressing at least the three major challenges. And the first one is that usually the function to optimize is a black function. That's not always true, but it's almost always true that we don't have a mathematical relationship between, for example, our molecular structures and chemical composition and the properties that we want to optimize. And other two issues is that normally the function to optimize is quite expensive. Either it requires experiments or expensive simulations, and that it's expensive both in terms of time and material. And also it's quite often the case that the search space is pretty large, that is kind of demanding. So very shortly, why Bayesian optimization is good is to solve these problems. First of all, it addresses the fact that we have a black box function by providing a statistical approximation with a surrogate model. So usually we have a Gaussian process as a surrogate model that actually has been largely introduced in the tutorial section. And the other things, it deals with large spaces because rather than sampling the whole search space in a systematic way and exploring all the portion, we usually have a policy that dictates which portion of the space we should explore, and that in Bayesian optimization usually is achieved using how to say, an auxiliary function, which is called acquisition function, which is always related to our surrogate model. So in this picture here, we see that at a given stage of optimization, we have a given a maximum of the acquisition function, and that is a criterion to tell us which portion of the space we have to explore, and this saves time. After, like in any active learning process, the model is updated, and then a new point is searched, and so on until a stopping condition is reached. Now this can be improved. Why is not? Can be further improved if instead of acquiring one point at a time, we actually design a new batch acquisition function which gives a finite number of points at each iteration. And then when it comes time to evaluate our objective function, these points, this can be done in parallel. So that, for example, is the case for design of experiment in chemistry. So, for example, in my project, the collaboration with a group which does chemical reaction with a robot, and the robot is designed to make experiments in parallel. So this configuration of Bayesian optimization is quite convenient to be applied to this case. However, there are in this case some challenges. So let's say the first one is that the batch points must be diverse from each other, because if they are too similar, basically there is close to no information gained by acquiring more than one point rather than only one. And then at the same time, these points must be useful to our task to find the optimum of the function. So we don't have to sample just whatever points as far as they're diverse, but the information is some kind of important parameter. Then another thing that we address in our work is that the search space is often discrete. And this is a problem at the moment because majority of the acquisition function have been designed for continuous spaces. There are some examples that where this problem is already been addressed, but it's still like an active topic of research. And then, as mentioned at the beginning of the conference, strong impact is given by the way that the molecules are encoded. So let's start from the first problem. Let's sample batch points as diverse as possible. So this problem can be reformulated like, okay, let's try to find a batch, a subset of our search space, which contains exactly a given number of point k. And these k points must be as diverse as possible. So what does it mean? So first we define a similar a criteria, we define a measure of diversity or similarity just by using the similarity kernel, which is basically the covariance matrix of between all the points which compose the batch. And then we say to compose the batch, we use a statistical stochastic sample according to a precise distribution, which is called L and some determinant point process. So what is that? So a point process is a distribution over a subset given the whole search space. And L and some determinantal process is a specific point process which is characterized by the fact that the probability of sampling of producing exactly one batch B is proportional to the determinant of the so-called diversity gauge, which is a quantity which is defined by this equation here, which is related to the similarity kernel. So it's quite convenient already that this distribution is related to similarity between molecules. It's even more convenient the fact that there is a mathematical way to prove that the batch which has the most diverse set of points is the one which maximizes the probability, which is defined by this equation, which is shown here on the left-hand side. So the idea to apply determinantal point process to Bayesian optimization is not ours. Our work relies actually on some work which is being published by the Welling group about permutations, and we apply here to the chemical space. So in that work, the goal was to maximize the diversity between points while at the meantime still keeping the informativeness of the points. So what the authors in this paper propose is say, okay, it's already been proved that if we use the posterior covariance of the Gaussian processes, it's a valid diversity gauge for determinantal point process. But the point is that if we use that only the posterior variance here, then we just maximize the diversity. We don't care about quality. So to enforce both, they define a new type of gauge, which is this one here, where practically it's a composition of the posterior covariance with the acquisition function A, and this W is actually a weight function. So this weight function determines the impact of the acquisition function. And then it's still possible to prove that the probability of producing a certain batch set is, if we define the diversity gauge like that, can be actually seen as a product of two terms, one which is enforced diversity and which contains the posterior covariance, and one which contains the acquisition function and enforces the quality. So we rely on that work. We choose a linear function of the acquisition function for our experimental settings. And we actually fix one term and we vary the B, which is the factor which tunes somehow the weight of the acquisition function. So the higher is B, the most the quality is enforced over diversity. We choose as our batch marked function some data set taken from the quantum data set. So these are very famous data set of organic molecules. And for each one, we choose a specific property. So we choose formation energy for QM7, band gap for QM7b. Then for the QM9, there are 14 properties. We choose the band gap and the polarizability. And then to explore the impact of the chemical descriptor, which I mentioned, that's quite critical in the performance, we choose two different configurations. One, it's used like column descriptors. Coulomb matrix descriptors. And actually, we adopt the eigenspectrum. So I think that people are quite, how to say, they know very well this kind of descriptor, which actually it's built based on the electric charge of the molecule. And which can we use? We just use like a simple RBF kernel, so the most commonly used one. But then we use another possibility with this, the SOAP descriptors. Now, this is quite long topic, so all the details can be found in this reference here. But very briefly, let's say that the SOAP descriptor represents molecules in terms of local environment. So given a molecule M1, a local environment is basically a group of atoms which is contained within the cutoff radius, starting from a given atom. And the peculiarity is that each atom is represented by its own density, which is described as a Gaussian distribution. And the local environment is, let's say, quantified or described by the atomic density, which is given by the sum of the density of the atoms. And then, of course, other transformation happens because there are requirements of rotational invariance. And let's say that the final result is that for each molecule, we have a SOAP descriptor, which is actually a kernel between this quantity which are mentioned here. And it's actually a matrix for each molecule. So for this, we need also to use another kernel because the RBF is simply not, cannot be interfaced with this kind of descriptor. And this kernel, actually, it's been designed exactly for this kind of descriptor. And basically, it's like a matrix which is being built on top of, like, I would say, by comparing the local environments between molecules. So now I pass to describe better the results, but it's not okay. So this is the results with the column descriptors. So each graph represents a different data set, and the black thick line actually represents another method, which is just which is the Thompson sampling, which is one method largely being used for Bayesian optimization in discrete spaces. And so we benchmarked against that, and we can see that typically for this kind of descriptors, our method it's quite more performant than Thompson. And this cannot be said the same about SOAP descriptor. First of all, you can see that generally the SOAP descriptors are give lower performance respect to column descriptors, and in 2 cases over 4 actually Thompson outperform our method if we use this descriptor. So we concluded that at least for this data set, the column descriptor works better if interfaced with this kind of Bayesian optimization flavor. So briefly here, this is a summary of what we concluded. So the parameter B, which is actually the impact of the quality over diversity, has an effect which is remarkably for all the data sets, only for Coulomb, while for descriptors that is not observed. And also, one thing to keep in mind is that the SOAP descriptors is quite expensive. For example, I don't know if you noticed that the results previously shown have only 150 iterations for SOAP descriptor that was doing like limitation for our computational time. And so actually more work needs to be done in the future to find out why the B, for example, parameter would be proven to be better to include the acquisition function rather than not including, why the parameter B doesn't show a clear trend, a monotonous trend. so that I'm finishing my PhD, so it will be the work for next one. And that's it for about the work that we did so far. So I want to thank you for your attention, and not if there is any time left.
Yep. Let's thank Simona. And we have time for questions. So are there questions?
Thank you, Simone, for the nice talk. My first question, so you had batch acquisitions, right?
Batch acquisition, yes.
Yeah. How large were the batches, and do your results depend strongly on the size of the batch?
We tried, for the Coulomb descriptor, we tried 3 different batch sizes, which are very low, 3, 5, and 10. But then we saw that actually the best was 10. But then in order to compare other work, so the work that is being shown here, it's actually only 3 because we have to find a way to deal with SOAP descriptor in a more feasible way. So the one thing that I didn't mention here is that actually the acquisition of the batch is sequential. So actually what you do, you just first sample one point with a normal acquisition function, the sequential one. Then you compute the determinantal points, adding a second one and then the third one. So it actually, the more point, because it's not parallelized, this process, the more points you acquire, the longer it takes. So for Coulomb descriptor was not too much of a problem, but for the SOAP one it was. And to make something like consistent, we went for the lower, but it's definitely improvement.
Okay, thank you.
Do we have other questions? Anything on Zoom? Okay. So maybe one clarifying question from my side. Was your objective to see how well batches perform, or were you trying to be faster than, or more efficient than, meaning learning faster than with a batch size of 1?
The objective was to be faster in terms of fewer iterations.
Okay, fewer model fittings.
Yeah, hoping that introducing, promoting more diversity with respect to normal acquisition function would have accelerated the process. Yeah. And this only partially true, unfortunately. So some other descriptor will be explored in the future, for example, given the fact that actually got different results with different descriptors.
Yeah, good. I see no further questions, so let's thank Simona again.
So I just, I need to, okay.
If you would, careful, you have the,